In 5.1, we are going to get introduced to the graphs of exponential functions. We're going to start with the table of values. And you have to remember some of your exponent rules from grade 9. What does the negative exponent rule do? If you have 2 to the negative 3, can you tell me as a decimal what the answer to this is? About. Can you round it for me? Is it about 8.7? Is it closer to 1.2? Is it closer to 0.3? Is it closer to... What is that number? Okay. So we have to remember our exponent rules. If you have a negative exponent, that moves that power to the other side of a fraction. So 2 to the negative 3 is like 1 over 2 to the 3. And if you do 2 to the 3, that's 2 times 2 times 2. That would be 1/8. So when I plug in negative 1/3, I get 1/8. If I plug in negative 2, it would be 1 over 2 squared. That would be 1/4, 1/2. Another exponent rule that's very important is what happens with an exponent of 0. It's equal to 1. Do we know why? Or is it just something you memorized? Okay. If it's just something you've memorized, okay, perfect, 2 to the 0. Anything to the 0 is 1. That's great. I'm going to give you a tiny little explanation that's pretty simple to explain why it happens. Because if you understand why something happens, your chances of remembering it are that much better. So here is a quick explanation of not only exponent of 0, why it's 1, but it will also explain why do we do this with negative exponents? Why do we put them on the bottom? How does that make sense? Okay, we'll start off with some exponents that you know. Right? These you can do with your normal exponent rules. This should make total sense to you, that 2 to the exponent of 2 is 4. Right? Is there anybody who doesn't know how the exponent works with repeated multiplication? That part's good, right? Well, mathematics is based on patterns. If I wanted to go up one more, if I'm following patterns here, and I want to put one above 2 to 3, what number do you think I put there? 2 to the 4. Did that blow your mind, or did you see that pattern? Now, if we look on the right-hand side, do you see a pattern there? What number am I going to put here? 16. Now, you know that 2 to the 4 is 2 times 2 times 2 times 2, but you also notice this pattern that you're doubling each time that you go up. But doubling each time you go up, you could also look at it as going backwards. If I continue the pattern here, 4, 3, 2, 1, what do you think I should put next? 0. If I continue the pattern here, divide by 2, divide by 2, divide by 2, makes total sense that it's equal to 1. And if I continue the pattern, if I go down one more, do you see you get negative 1? And if you divide by 2 again, you get a 2 on the bottom. And if you go again, you get 2 to the negative 2. If you divide by 2 again, you get 1 over 4, which happens to be 1 over 2 squared, which explains the negative exponent rule as well. So having that in your mind, now hopefully you won't forget that anything to the exponent of 0 is 1. And then these ones are easy. This will be 2 to the 1, 2 squared is 4, 2 cubed is 8. If we plot these points, we notice the following. We've got that 0 is 1, 1 is 2, 2 is 4, 3 would be 8, which is up there. This is a half, then a quarter, then an eighth. And we've got a shape that is starting to form. And that shape ends up looking like this with a horizontal asymptote at y equals 0. that x gets towards the negative infinity, the bigger negative number that x gets. So if I do 2 to the negative 100, that's the same as 1 over 2 to the 100, which is a huge number on the bottom, and it gets very, very close to 0, but never touches 0. That's the idea of an asymptote. So this is the graph of y equals 2 to the x. Are we going to review chapter 1 and do all the transformations with these? Absolutely. You're going to take this as a new parent graph and graph anything. But the interesting thing about the parent graphs of exponentials is there are also an infinite amount of parent graphs. Because we just drew 2 to the x. But you could also draw 3 to the x, 4 to the x, 5 to the x, 6 to the x, 7 to the x, 2.735, 4 to the x. They are all new parent graphs. So as far as labeling our parent graphs go, we are always going to label 0, 1. Because no matter what the base is, a base of 2, like this one, a base of 3, a base of 5, they will always have 0, 1. And the easiest next point to label is if you plug in 1 for x. And you see that in this case you get 1, 2. Pick a number other than 2. 10, 3? Okay, yeah. So if we had to graph y equals 3 to the x, this is how we're going to do these quickly. For sure, it's going to have 0, 1. Because anytime you plug in an exponent of 0, you get 1. And the second point we're going to label is 1, 3. It's going to have the same shape as before, and it's going to always have an asymptote at y equals 0. So now you can graph 5 to the x. It would have 0, 1 and 1, 5. And then we're going to do our transformations, stretches, compressions, shift it left, right, up and down. All of that we get to review with these graphs as well. What happens if the base is something like a half? Again, I'm not even going to do the table of values. We're going to use that same strategy. Does it make sense that you will have 0, 1, even though it's a fraction? Now what happens when I plug in 1 for x? I would get 1, half. Does that make sense? So this has the same idea of a shape, but it's going in the opposite direction. In fact, you might recognize that it's the same graph that we drew in part A, just a horizontal flip. Okay? Transformations, how do you do a horizontal flip? There would be a negative with what? In front of the function or in front of the x? Right? Horizontal would be in front of the x. So, watch this. If I take y equals 1/2 to the x, algebraically, I can change this 2 on the bottom, which technically would have an exponent of 1. Anytime I move something to the other side of a fraction, that's my negative exponent rule. That would be 2 to the negative 1. 1/2 is 2 to the negative 1. And an exponent to an exponent, that's an exponent rule. You multiply them, sure enough. You get 2 to the negative x, which is just a horizontal flip of the 2 to the x graph.